Okay. Good afternoon, everybody. So thanks a lot to Christophe and Janaina for inviting me and putting all this together. So I'm going to talk about learning from multimodal data for disease prediction. So the idea is basically to try to guide you through the literature. So when you do a PubMed search for, let's say, machine learning, MRI, and Alzheimer, you get 147 references that are mostly relevant, and that's only one disease, and that's only MRI. So the idea is to try to guide you a little bit into this, to help you put papers into small boxes where you know where they belong. So I'm going to touch about multimodal data, so anatomical MRI, PET, but also diffusion MRI and functional MRI. For the specific task of disease prediction, so it's going to be quite different from most of the talks on brain decoding from fMRI data. So starting with the basics, so a common way to set the problem is that of computer-aided diagnosis. So for a given patient for which you have neuroimaging data, you would like to predict an outcome that can be, for example, a binary label like Alzheimer's or controls. And you want to learn a discriminative or prediction function that is going to predict this outcome. So for example, a diagnosis. Usually you do that with a supervised learning approach where you have a training set in which the diagnosis for the end subject is known. If the outcome is binary, it's going to be a classification task, but it can also be continuous, where you try to predict a cognitive or clinical score, and this is then going to be a regression problem. You can do that from a single modality, so for example, anatomical MRI, or you can do that from multiple different modalities. Another type of problems we can be interested at is, let's say, to try to help redefine the boundaries of neurological disorders. Starting with the idea that the current definitions of these disorders are unsatisfying because the clinical diagnoses have limited reliability. The boundaries between the diseases themselves are fuzzy. They are not well defined. And finally, the clinical syndromes, so for example, memory impairment, only partly overlap with pathophysiological processes. So for example, the accumulation of a given abnormal protein in the brain. So then the question is, can machine learning help to redefine those disorders? So that would amount to try to find clusters in a population. And usually this would amount to unsupervised or semi-supervised learning approach. So in my talk, I will mostly focus on the first version, so the sort of computer-aided diagnosis, and I think Janaina is going to talk at least a bit of the second types of question. So the main types of applications would be to try to diagnose disease at the early stage, to try to predict future cognitive decline, or to try to stratify populations into more homogeneous clusters. So this is important to improve therapeutic trials. For example, in neurodegenerative disease, it's very likely that if trials are to be successful, they need to be applied at the very earliest stage, probably pre-symptomatic, but then you would need to be able to identify the patients that will rapidly evolve to disease in order to include them in the trial. This could improve clinical diagnosis as well and develop precision medicine. So in this talk, I'm going to take Alzheimer's disease as a prototypical example, mostly because it's probably the disease for which these approaches have been the most developed. So the most simple learning task you can work with is simply trying to differentiate between patients with Alzheimer's disease and controls. It's a relatively easy task and methods work well. Or you can try to do more interesting things like predicting the evolution from, let's say, prodromal or even pre-symptomatic stages of patients. So usually that will involve patients at early stage. So for example, having MCI, mild cognitive impairment, that are followed over time. And then you can set this problem either as a classification problem, separating progressive MCI from the patients that remain stable, or, and it's a better way to set the problem, as a regression problem where you try to predict the time of onset or the future clinical score. And in this disease, the main types of data that are of interest are anatomical MRI showing atrophy, and in particular loss of gray matter, PET with different types of tracer, FDG, which is well established because it's a very good predictor of rapid cognitive decline, but also pathophysiological markers that are specific of the disease, such as amyloid or tau PET, that allows to map in the brain the protein aggregates of amyloid beta or tau protein. So the main components of this kind of approach are relatively standardized. Starting with an image, there is a feature extraction step, then often a feature selection step, and finally the learning itself. I'm going to show it briefly in the case of anatomical MRI so that we are all on the same page. And basically the different methods fall into the following categories. You can, the four types of features are voxel-based. Each subject is seen as a collection of values at each voxel of the image. So classically, for example, a map of gray matter that is segmented. Of course, you have to do inter-individual registration to bring all the subjects into a common space so that to achieve correspondence across subjects at a given voxel. So at the end, you will work with a vector X in RP, where P is the number of voxels in the image. You can apply exactly the same idea on the cortical surface, where now your features are the collection of values at all the vertices of the surface. So typically, for instance, cortical thickness maps. And a third relatively common type of features is regional features, where you label the brain into different regions. So usually anatomical regions. You take one or several features in each region. So for example, the volumes, the average thickness, average gray matter value, or more sophisticated descriptors. And then you end up with a vector X in RP, where P is the number of regions. You can do that with many types of atlases. So if you don't know, you can, for example, go at this website. It's a good reference of the available atlases for cortical and subcortical structures. Sorry, I clicked on the link, which was probably not a very good idea. There are also more, let's say, exotic types of features, such as, for example, deformations. The motivation for that is that all the previous approaches are based on the idea of localization. So each feature will correspond to a given location in the brain, let's say a specific voxel or a specific region. But it is true that actually a large part of anatomical variability cannot be localized. Let's say, for example, if you have a displacement of a given sulcus or gyrus, a localization approach will mostly show you that this as a disappearance or appearance of this gyrus. So another approach is to use as features deformations that would map a template or an average anatomy of, for example, a collection of anatomical structures onto each subject. So at the end, the features are not the characteristics themselves, but the deformation that maps the template to each of the subjects. Depending on the way you define your deformation, it will lead into a space where you can apply classical machine learning algorithms, such as, for example, kernel methods, if you have a kernel defined on your deformations. Also, these are the main types of features for anatomical MRI data. So just to summarize a little bit for the beginners, and to give you a brief classification of different learning algorithms. So what you want to learn is a function f from your feature space to R, where R can be a continuous or a binary output. So typically this will, you try to find f that is going to fit your training set, minimizing some loss between the outcome you want to predict and the prediction. Very classically, in neuroimaging, you are in a high-dimension, small sample size problem, so where n, the number of subjects, is much smaller than p, the dimension. So the classical approach to tackle that is to control the complexity of f so that you subject your minimum to a regularity or a sparsity constraints. Alternatively, you can also write that as a compromise between your data fidelity term and your regularization or sparsity. Depending on the loss that you choose, you can end up depending on the loss that you choose and depending also on the regularization that you choose, you will end up with different algorithms. So here, for example, this with the L2 norm and this loss, you will recover ridge regression, and with this loss, you will recover support vector machine. You can also apply sparsity inducing norms, such as, for example, the L1 norm in the lasso algorithm, or combination of different norms, such as, for example, in the elastic net regularization. Typically, using a single modality, these are the results that you can get in an Alzheimer's disease application. So here, the methods will perform relatively well for the simple task of Alzheimer's versus controls classification, still relatively well for identifications of patients at the earlier stage, but relatively bad for progression, for prediction of progression. So the natural idea, since anatomical MRI is not a very good predictor of future progression, is to include a multimodal data. So why do we want to do that? In Alzheimer's disease, it's, for example, relatively natural because these modalities convey different types of information. Anatomical MRI is relatively a good correlate of the progression of cognitive deficits, but it's a late stage. It doesn't anticipate that much on the deficits. And also, it's not biologically specific. So it doesn't tell you anything about the underlying molecular pathology of the disease. On the other hand, PET, for example, using amyloid tracer, is biologically specific. So it's specific of Alzheimer's pathology. But on the other hand, it's so early that it reaches a plateau many years before disease onset. So it itself is not either a very good predictor of short-term conversion. So then, how do you combine these different modalities? So there are several ways to do that. The first way is to extract features separately for the two modalities, and then to enter them simultaneously into a learning algorithm. A second type of approach is to do the learning separately for the different modalities, and then to do a fusion of the decisions, for example, of the outputs of the classifiers. The different types of features that you can use can be first relatively similar to that you could use for anatomical data. So, for example, at the voxel level, where you see the subject as a collection of values at each voxel in each of the images. At the region level, where you average the signal or measurement within each region. But in that case, usually you would want to use different types of analyses for the different modalities. For MRI and PET modalities, it's relatively common to use the same atlases as the signal of interest is mostly in cortical regions, at least in the case of Alzheimer's disease. But for diffusion MRI or functional MRI, different types of atlases exist. So for example, for diffusion MRI, the relatively common ICBM DTI 81 atlas that is available in FSL, but also functional MRI atlases based on functional MRI data. Another types of features that is relatively natural also, in particular for fMRI, EEG, and diffusion MRI, is to use graphs where you would encode the connectivity between distant brain regions using a graph. And then for machine learning applications, you can either use the graph directly, but then you will need to have an algorithm, a learning algorithm that can work on graphs. So for example, you can use kernel methods for which you have graph kernels that are defined. Another way to proceed is to summarize the information conveyed by the graph into network indices that will characterize the global and the local topology of your network, and that you can then treat as scalar measures that you enter in your learning algorithm. Ways to do the integration of different modality. One way to summarize them is that you can integrate the modalities at different stages of the procedure. You can do an early integration where you just concatenate all the data together. You can do an intermediate and late integration. So the late integration would be learning separately on the different modalities and then combining the outcomes to produce a final decision. Or you can do also an intermediate integration, which is, for example, often done using kernel methods, where you will define a combination of the different kernels that correspond to your different modalities. So here, for example, I take an example of multiple kernel learning using actually Gaussian processes for Alzheimer's disease prediction that defines separate kernels for MRI, PET, but also genotype data that learns a combination, here a linear combination of the different kernels for the different modalities. And what you can find is that actually the combination of MRI and PET slightly improves the accuracy of the prediction. So that was mostly for the methods. Now let's talk a little bit about the validation of these approaches. So I think it's important to be aware that even though there is a very large number of publications, mostly in the medical image computing field, the validations of these have been so far been insufficient. First, the data sets are too small, and I think we touched on this also this morning. It's relatively clear that with this type of size, you get relatively large error bars that are, in particular, very insufficient to draw clear conclusion on which approach performs best. So we need larger data sets. One other problem, and that I think is a very severe problem, is that most approaches have been validated on the same database. In the case of Alzheimer's disease, this database is ADNI, that you probably know, which has been a blessing because it's publicly available and it has generated a lot of research. But it has also been a sort of curse in a sense because since there are only few public data sets in the field, all the methods are validated on the same data, and it's relatively unclear how they would generalize to other data sets. So we need more public data sets to validate. And even worse, actually, methods use the same database, but with different subsets of patients. So you could have the advantage of having the same database. You could think that at least you can compare, but actually it's not true, because everybody is using a different subset of the ADNI. Why? It's not clear. Is it really cherry picking? Sometimes it may be just convenience, because it's actually the data management is relatively difficult to do with ANI. So at the end, it's very difficult to compare the performance. So we need more transparent and standardized selections. And finally, one last important drawback is that most of these has been done with data from research studies. So that means patients that fit specific inclusion criteria where the image quality is well controlled. So usually the imaging protocol has been harmonized across different centers to ensure homogeneous quality. It's not clear at all how the performance of the methods would be on clinical routine data, where the quality of the data is much less controlled, but also the patients are not selected with strict inclusion criteria, but have mixed pathologies, can have, for example, depression together with Alzheimer's disease, or vascular disease together with neurodegenerative disease. So we need more clinical routine data sets to do that. So to try to do a little bit more better validation, there have been some comparison papers that have compared different types of approaches for prediction. So I set here just a few of them. The advantage is that it's relatively unbiased and is standardized. At least it's on the same set of patients. And it's controlled so that you can study the influence of specific parts. So, for example, you can see is a feature matter more than the learning algorithm or these kind of things. So drawbacks is that first it's a static evaluation in the sense that it's done once and for all. It's a paper. They select a set of methods and a database, and it's not going to evolve over time. It's limited to the approaches that are studied in the validation. And most often, it's limited to a single research data set, very often ADNI. So on the other hand, there have been some challenges, in particular in the field of Alzheimer's disease. So I cite a few of them that you might know of. So there was this CAT dementia for 3-class diagnosis at MICAI 2014. There was this DREAM challenge. There has been a few Kaggle challenges too in the field of Alzheimer's disease. And finally, there is a current challenge that just opened, that is this tadpole challenge for a prediction of short-term conversion of Alzheimer's disease that you want to look at. The submission deadline is in November. So the advantage, again, is that it's unbiased. It's the same set of patients. Compared to comparison paper, the advantage is that any group can contribute, so the methods would probably be more varied. Limitation is that, again, it's usually a bit of a static evaluation. Some of these challenges continue over time. So they can get new contributions and submissions, but it's not always possible. So, for example, the tadpole challenge is based on future evolution of patients in the ADNI data. So once the data gets out and is used for evaluating, then it's not really possible to continue to use it for new evaluations. Again, they are often limited to a single research data set. And finally, one thing that is also important is that in some of these cases, it's quite limited in terms of features. So, for example, some of the Kaggle challenges for that, they only give you a set of pre-extracted features. So, for example, free surfer ROI measures. And that's the only thing you can work with. So it might be interesting for machine learners, but for neuroimagers, I think it's a bit limited. So to conclude, there is really a huge body of literature on the topic of computer-aided diagnosis using machine learning, in particular for Alzheimer's disease. And one reason is because of the ADNI. Because it's available, it's not too small, and many people have worked with it. Predictive powers remains limited in challenging cases. Papers report good accuracies for prediction of evolution, but it's still not clear how they would perform on clinical routine data and how they would generalize across different clinical centers. Clearly, multimodal data has the potential to improve prediction, but it's still not entirely clear how this should be combined. In particular, for Alzheimer's disease, little attention has been paid really to the different nature of the information that is conveyed by the different types of modalities. And finally, as said, validation has been insufficient. We need more public data sets. We need larger data sets. A few hundreds of subjects is not enough. We need more transparent and publicly available validation procedures. And finally, we need more clinically realistic evaluations. So research data sets are a good first start, but are not enough to assess how methods will work in a clinically realistic setting. So thank you for your attention.
Olivier, thank you. It's very direct. When you have different features for different sources, functional, structural, you have different features, and you mentioned that you can combine them, and there are at least 2 or 3, 4 ways to combine. You can combine the beginning, later, or after. Why there are so many possibilities? And what are the difference between them in terms of the performance and in terms of the applicability as well?
Why are there different possibilities? Just that it's different, I think, natural ways to combine. So the first approach is simply to put everything together and to treat each modality in the same way. Usually that doesn't work very well. The last approach is also relatively natural, is you learn something separately and you try to combine the outcome of your learning algorithm. So for example, you can learn if, according to anatomical MRI, your patient has an Alzheimer's disease pattern. You can do the same thing for FDG PET, and then you combine the decisions, or let's say the results of the two classifiers. The intermediate stage is that you try to define, let's say, a metric or a way to handle each type of data separately. So, for example, a relatively natural way to do it is with kernel methods, where you would define a kernel that you can think of as a dot product or as a similarity measures between your subjects. The advantage of doing that is that you can choose different kernels for the different types of data. So for example, suppose that you're convinced that regions are the best way to look at anatomical MRI and that graphs are the best way to look at functional MRI. I don't know, I'm not advocating that, I'm just saying if you are convinced of that, then you can build kernel for the two modalities and combine them. The drawback is that you have also to learn the combination. Or you can fix it, but then it's maybe not very flexible. And if you have to learn the combination, well, then it's more flexibility, so also more risk of overfitting. And is that clear?
No, it's clear. The method is it's clear. The thing that arises, for example, if you choose the late, you are clearly putting a new. You have a prior because you know this image or you know that sources could be better for this or that
Okay.
I would say this is a new information that came from the researcher.
Yeah.
So this is the point. If you choose the first one, excuse me, if you choose the first one, you are just trying to see something what comes from the data.
Yeah.
So both procedure does not seem to be identical, or at least.
No, of course they are not. In one case, in the late case, you assume that at least you can learn something meaningful from each data separately, and that by combining these decisions, you would produce something that is better than each of the decisions separately. In the first case, you don't assume that, so it could be that you can only learn when you put the different modalities together, that only something meaningful would come out when you combine the two. That, for example, atrophy in itself is not meaningful, but it's only when it's combined with some other things. But this comes at the cost that you increase the dimensionality, you put everything together, so you treat all the features of all the modalities in the same way by concatenating them. And in practice, it's not really clear that this works very well. Is it? Okay.
Last question before we move on.
Just a follow-up on that. So you mentioned that getting kernel from, let's say, one modality and getting a kernel from other modality, that you can combine that into one kernel, and you give an example of graph kernel, but you didn't really explain what it does exactly. So my question basically was, how do you really interpret? You have one similarity matrix from one modality and similar similarity matrix from another modality. You fuse them together, you get one final kernel for running classification.
Yeah.
So are you basically, of course you're ultimately going for prediction, diagnostic prediction. But how are you going to interpret that? It's just, how are you fusing the two modalities? What should I interpret from like fusing one similarity, one gram matrix from another gram matrix?
Yeah, absolutely. So that's that's another thing. When you stay in the when your input space is the feature space, so in the case where you just concatenate, the advantage is that it's easy to go back and interpret the coefficients of your decision function in terms of the. When you work with a nonlinear kernel, you cannot do that anymore. So if you want a direct interpretation, for example, on graphs of your classification, you are probably better with working with graph indices, so extract indices. For example, I don't know, modularity, clustering coefficient, whatever you want. And then you can apply a linear kernel and go back to these features and interpret them. The graph kernel itself, as far as I know, is not going to be very interpretable. Nevertheless, the advantage is that you will not make a prior that a specific type of graph features is more useful or more discriminative.
Thank you.